I am a professor at Tata Institute of Fundamental Research, just another 10 minutes down south from here. I work on astroparticle physics. What I'm going to talk about is also a part of that field of research. My aim here will be to do two things at the same time. On one hand, I want to tell you a little bit about this thing called dark matter, what it is and how do we know that it's there. And on the other hand, I also want to give you a sense of what is it like to do science. What is it like to be a practicing scientist? What's the kind of day-to-day activity that we indulge in? As a theorist, I'm not an experimentalist, I'm a theorist. You'll realize that there's a difference between the two if you don't already. So these are the two parallel tracks that I want to go on. I want to tell you about science, dark matter, and I also want to tell you a little bit about what is it like to do science, what's the type of mentality that you need to do science, what's going on at the back of your mind while you are doing science. Okay, so keep that in mind while I talk, and feel free to ask me questions. Anything that I don't explain clearly, it's my fault. Feel free to ask. Bejhijak, besharam, behaya hoke puchiye. Or the other thing is, in particular, if I use some jargon, some particular word that, sometimes we can't help it, we get so used to these specific words that, I'm not thinking that I'm being very technical, so just stop me right there and, make me explain things. Alright, so let's start. Right? So, this is a familiar picture for everyone, right? Everyone knows what this is. Who here doesn't understand what this picture is? Is there anyone?
Yes.
Now you know. Now you know what this picture is?
No.
No? Alright, so this is where we are. This is Bombay.
Oh, yeah.
Alright, now everyone knows. Alright. Now, this is Bombay. We immediately recognize what the rest of this picture is. How many of you would say that there is nothing out here? So this part which is dark, how many of you would say that, there's nothing out there, it's empty? Is there anyone who would say that here? No, right? We know that although there is nothing that we can see over there, it's not actually empty. But this familiar intuition breaks down when I show you a different picture. So instead of looking down at the earth, let's look away from the earth and let's show you this picture. So this is a picture of the sky. This is an arm of the Milky Way. This is our familiar territory. Now you see these dark patches. What's the natural feeling that comes to your mind? Is that empty or not?
Empty.
Empty. The natural feeling is that must be empty, right? Okay, now I'll show you an even better picture. Right? So now this is just a same picture. So you take this picture and zoom in on one of these dots over here. Each of these dots is a galaxy. Okay. So I zoom in on one of these galaxies. This is called the pinwheel galaxy. It looks like this pinwheel that children play with, right? So astronomers sometimes get creative and use these funny names. Okay, so this is the pinwheel galaxy, and now this intuition is even stronger, right? So if I tell you that, look at this region, this looks dark, is it empty? How many people would feel that, okay, yes, that's empty? Show of hands, please. Empty, not empty?
It looks empty.
Empty. Most people think that it's empty. But that's actually not true, and that's the whole point of this talk. So this is an even more zoomed out picture of the universe. So what I have shown here is that this object is a galaxy and it's 100,000 light years big. So just in case someone doesn't know what a light year is, a light year, although it ends with a year, is not a measure of time. It's a measure of distance. What is this distance? A light year is the distance that light covers in 1 year. And so now, if light travels for 100,000 years, that's the distance that light would cover, and that's the size of this galaxy. A galaxy is a compilation of approximately 1 billion stars, typically. Okay? So that's the size of this object. And here, I have 100 million light years. So this is a really, really wide angle picture of the universe. Okay? Each of these dots that you see here is a galaxy, and there are these web of galaxies that we live in. Somewhere in this web is the Milky Way. Inside the Milky Way there is a star called Sun. Around that Sun is a planet called Earth. On that planet Earth are us. So somewhere in this picture we're there. Except that this is not a real picture. This is a picture that's generated using a computer. I'll show you a similar picture which is real somewhat later. But the point that I'm trying to make here is that this is what the universe looks like. Almost 100 million light years wide. The universe isn't much bigger than this actually. And if you pay attention, maybe you can see there are these fuzzy, bluish regions between the yellow dots. Can you see that? I don't know. I mean, the lighting is perhaps not very good.
No.
But maybe you can make out this fuzzy gray color here. What has been done is that I have, because this is a computer generated image, I have false colored where there is dark matter. Now I haven't told you what dark matter is or how I know that this picture is true, and we'll come to that. But I want you to have some intuition of what dark matter looks like, in the universe. And this is what it looks like. So the yellow stuff is what you see out there in the sky. If you had a big telescope, the yellow stuff is what you would see. But if you could see dark matter, you would see that this yellow stuff is like jewels which are encrusted on this fuzzy, filamentary-like thing which is shown here in this grey or bluish color. This is the stuff that we can't see, but we know that it's out there. And so the rest of the talk will be about how do we know that it's out there, and what can we do to find out what that object is made of. So we will talk about the fact that this stuff, whatever it is, this dark stuff, cannot be any of the stuff that we know of. It cannot be made of the atoms that we know. It cannot be anything that we know already. It's something new. Okay? And then the question will arise, what is that new thing? So that's the second half of the talk. The first half, I want to concentrate on telling you, how do we know that there is such a thing? And that should give you an indication of what is it like to do science. Because here is a bold claim that I am making, that there is this invisible, fuzzy stuff out there in the universe. And now I have to justify that claim. I have to give you evidence that will convince you that this is not just a random bold claim. That this is a claim that's backed up by data and by logic. So let's tell you a little bit about how do we know that dark matter exists, and then what is it made of? Okay? These are the two questions that we want to answer. The key idea that we will use is motion of an object can measure the mass of other objects. Okay? This is the key idea. We will use this idea to infer that there is stuff out there in the universe that we are not able to see. Okay? So the key mantra, if you will, is motion measures mass. And now we will show that this simple idea allows us to infer that there is this matter out there which we can't see, but we know that it has to be there. Okay? So before we get to dark matter, let's do a very simple example. So this is Professor Isaac Newton. He's standing on Earth with his favorite fruit, the apple. And there are two of his favorite equations up there. Okay? So everyone has learned this in school. F is equal to ma. This is the second law of motion, Newton's second law of motion. And F, the force, is some constant called universal constant of gravity g times mass of the two objects divided by the distance between them squared, which is the gravitational force between the objects with mass m and small m. Okay? So these are two of Newton's equations. This is Newton's law of gravity, and the second one is Newton's second law of motion. Everyone knows these things. Okay, now what these two equations allow you to do is measure the mass of one object by looking at the motion of another object. So let's explain how that happens. So let's say my friend drops this apple from his hand. You know what will happen. It will fall down towards earth. This is some distance, let's call that h. Some distance, it's let's say a meter in height. And if I drop this apple, it takes roughly half a second to hit the ground. Knowing these two things by doing an experiment actually allows me to measure the mass of the earth. So let's see how. So there's some little bit of high school algebra to do here. But even if you don't want to go through all of that, there is a simple formula for height as a function of time t. You know this number a somehow, and as a result you can write down that the mass of earth is related to the radius of earth, which you can measure, and the height from which you are dropping the apple, and the time it takes. Okay? So there is some little bit of high school physics to do. Doesn't matter, what exactly in detail this is all about, but the key idea to understand here is that the motion of the apple allows me to measure the mass of earth. Okay? This same idea can now be used to measure the mass of other objects in the universe. Now this is a very bold claim, if you think about it. Because we are saying that these are certain, physics laws that we have found out on earth. We will use these same equations elsewhere in the universe, somewhere out there, and hope that they are correct and that they work. Based on that, we will learn new things about the universe. And so this is one of the very interesting things about physics, is that we believe that the laws of physics hold true everywhere in space and at all times, that these laws are unchanging. These are eternal laws, universal laws everywhere in the universe. So this idea allows us to learn about things away from us. Astrophysics typically deals with things which are very far away from us, but we use the laws of physics that we have derived or understood on Earth to understand things which are very far away from us, on which we don't have any direct control. We can learn things about the sun or some black hole which is far away without actually going there, simply because we are applying the same laws that we've learned here on Earth. So that's one of the things that scientists will do. Alright, so we'll use this idea to learn about dark matter. So there are 5 completely different ideas which tell us that there is such a thing as dark matter. Okay? So this is the first one, and this is historically the first one that was done. Now this will look complicated to most of you, but again, remember, I want to do 2 things. I want to tell you about dark matter, and I also want to give you guys a sense of what is it like to be a practicing scientist. So when you are a practicing scientist, you make things like this, these things are called plots. You make these plots, and these things tell you, interesting scientific things about the universe. So here actually it's a very simple picture. Here on the x-axis is the latitude. On the sky you write down what the latitude in the sky is, and here is the longitude. And each of these points is actually a galaxy. Okay. Now there are lots of dots here. Each of them is a galaxy, and I have colored the galaxy by the speed that it has. Every galaxy is zipping about, and each of them has a speed. So I have colored the slow ones with red color and the fast ones with blue color. Okay? Now you can see that there are quite a few galaxies which are very slow, but there are also a bunch of galaxies which are quite fast. There are a bunch of blue dots over there. This is telling you that there is a difference between the velocities of these galaxies which are there as a part of some cluster of galaxies. This can only be true if the total mass contained in that object is fairly large. Why is this so? So think about taking a piece of stone, tying a string around it, and then whirling it around. If you want to do this, and you want to do this also for another piece of stone which is moving very slowly, the only way you can do it is you are pulling these two things at very different with very different forces. Because if you are trying to whirl it in a tiny circle over here, you will need some small amount of force. If you are trying to pull it with a very big circle, you will need more force. Okay? So which means that the amount of force that you need to move something around, what speed it has, depends on how much gravitational pull it experiences. So the fact that there are different classes of stars, galaxies, some very slow, some very fast, tells you that there is a big range of gravitational forces acting on things. That tells you that in this big object actually has a lot of mass. Okay? And so from that you can measure the mass, and that mass turns out to be 400 times larger than the mass that you can see in stars and galaxies and gases. So what happened is that Fritz Zwicky in the 1930s, he was at Caltech, he did this experiment, he measured these galaxies, and he found that the only way he could explain the motion of these galaxies is to say that there was 400 times more mass in that cluster than what could be seen at that time. So this was a very bizarre and confusing thing. He called this missing matter dark matter. Dunkelmatter is German for dark matter. So he said that there must be dark matter which far exceeds the light matter, the matter which is visible. So this was the first indication that there was dark matter. This was in the 1930s. Since then, there have been many more interesting and easy to understand ways that there is dark matter. One of the easiest ones is this. We know that the Earth goes around the Sun. It takes some amount of time, which means that the Earth has some speed around the Sun. Alright? Now, all planets actually go around the Sun and they have some speed. So what I have done is I have shown various planets and other objects with their distance from the Sun and what their speeds are. As you can see that when things are far away, they have smaller speeds. Okay? Because everything is being attracted by the Sun. And so there is this very well-known curve that these planets trace out. And so this is very well understood given the laws of physics, Newton's laws of physics. Now, when you do this with galaxies, something weird happens. So these are two galaxies. On the left, I am showing you what would be expected out of Newton's laws of motion. And on the right hand side, I am showing what actually happens when you actually observe the galaxy. The speed of rotation around the center of this galaxy, we expect it to fall down based on what we just saw with orbits of planets. So now I'll just show you a little video. This is a simulation again. And you will see that this expected galaxy is rotating very slowly around the edges. But what you see is that this is actually moving much faster. In fact, the edges are swirling at exactly the same speed as the center. So I'll play that again, and as you can see. See, the speed of something here is more or less the same as the speed of something over here, and that's what's seen. This is often called that the rotation curves of galaxies, the rotation as a function of radius, is flat, that everything has the same speed. Okay? Whereas what you would expect based on physics that we know and understand on Earth, by doing lots of experiments we've determined these laws, is that the speed should decrease. Now you can explain this contradiction only if you assume that there is a lot of mass all the way outside the galaxy which is not being seen. Then that invisible mass or dark matter would make the galaxy rotate faster, because now there is more gravitational force and things can go faster. So this is the second way in which people understood that there has to be something called dark matter. These are called rotation curves of galaxies. This was actually discovered by Vera Rubin with her advisor Kent Ford. And I want to just make a little point about women in physics and science in general here. In astronomy, by the way, a lot of very big discoveries were made by women. So pulsars was discovered by Jocelyn Bell Burnell. There are many astronomers who did calculations for NASA missions. So women have played actually a very strong role in astrophysics. Unfortunately, because of societal reasons, often you don't get to hear their names. But Vera Rubin is one of the big superstars in this field, and she is alive and well, and she is working in physics still now. And this is her before she actually went to university. This is her at Vassar College, and she was discouraged to do science even at that age. You can see that before she went to university, she's looking through a telescope. So she clearly had a passion for science. But even at that point, she was discouraged. Okay, science, physics is very hard, don't do it. But she didn't listen to people, so that should be a lesson, I think, for people. Okay, so the two ways of doing dark matter, we've already told you how we know there is dark matter. I'll tell you of three more ways by which we know dark matter. Why am I doing this? Why am I harping on this point that I'm going to really convince you that there is dark matter, and not by using one argument or two arguments? I'm going to tell you about 5 different arguments why. Why? Because that's one of the hallmarks of science. That you don't believe something with just one simple argument or a simple experiment. You want confirmation, and you want overwhelming confirmation. You want confirmation that cannot be doubted by anybody in the community. You cross-check the same thing from 5 different ways and make sure that you get a consistent answer, a very consistent picture based on all the known facts and all known laws of physics. That's one of the hallmarks of science, that we like to have a very unified picture of everything. That no matter which direction you look from, the answer should be the same. Okay? So 3 more ways. These are a little bit more subtle. So I'll try to do my best to explain these things. So this has to do with bending of light. So usually when we shine a torch, we always see that the light goes in a straight line. But this is actually not completely true. The earth actually is attracting, just like when we throw a ball or an apple and it falls down, the earth is also attracting light, and the beam of light isn't actually going straight, it's bending a little bit downwards. Okay? We don't get to see that because this effect is very small. But this effect becomes quite large when the object that is doing the attraction is not Earth but some big objects like a black hole or a big cluster of galaxies. Okay? So this is a particular scenario. So where we are here on Earth, there is a very far away galaxy with a very bright star, and between us is a very big, massive galaxy cluster. And it's a cluster of, let's say, 1,000 galaxies. There's a lot of mass in here. And when there is mass, Einstein's theory of relativity says that space-time around it bends. Many of you might have seen this movie Interstellar, which shows what happens around a black hole, where the space-time gets bent because of the effect of the black hole. It's exactly the same thing, not as strong, but a big cluster of galaxies can make space-time around it distorted, and that bends. It's exactly the same way as when you have, let's say, a rubber membrane and you put some big, heavy object in it, then the membrane bends. So we think of space-time also as this big membrane inside which we are sitting, and when you put a big mass somewhere, that bends space-time. Now, because the space-time is bent, light will still follow the straight lines on this bent path, on this bent membrane, if you will. So let's say I think of this floor as space-time, and I have drawn straight lines on it. Now if I put some big mass on it and then the floor gets warped and bent, light still follows the lines which are already drawn on these. These things are called geodesics. These are the lines of shortest distance between 2 points. And so light is still taking the shortest path between 2 points. But seen like this, it seems like the light is bent. Okay? Now, the light is bent around these massive objects, and sometimes what can happen is that because this, let's say, between me and you, there is a very massive object, there are 2 equivalent shortest paths. Okay? So I could go this way or that way. What that does is makes multiple images of the same source. So this is called lensing. So this object, this big cluster of galaxies acts like a gravitational lens. Now, it's a lens which acts on light through gravitational interactions because of its effect on mass. So then what happens is that the light from here gets bent exactly like the lens that we know, like one in this projector for example, and you see multiple images of this galaxy. And using this, you know that there was a lot of mass over here. The fact that the light from a star got lensed tells you that there was mass in the middle between you and the source. Okay, so let's use this idea, and what can we do with it? So this is a picture, this is a real picture of the sky taken with a telescope, and all that has been done is that it has been colored using some false color. So the yellow points that you see, these are all galaxies which are far away. Okay? But they are not all different galaxies. Many of these galaxies are actually the same galaxy which is showing up more than once because there are multiple images which have been lensed by something in the middle. How do we know this? Because we can measure the light coming from each of these sources and they turn out to be exactly identical. So we know that, for example, this and this are not two different galaxies. They are actually the same galaxy, but they have been seen twice because there is some mass over here which is making this lens. In fact, you can see it in another way, that there are a lot of curved lines here, like circular arcs, which are all circumscribing this hazy thing in the middle. Okay, this hazy bluish grayish thing that has been shown here, that actually can't be seen. That has been put in by hand after looking at the shapes of these galaxies and using them to reconstruct how much mass there must have been in the middle. So this is a false color map of the dark matter which is between the faraway galaxies and us. Okay? So what's happening here is that these curved galaxies are allowing us to measure the mass between the source and us. So again, think about it, what I just said, that motion allows you to measure mass. Now, the motion of light between that source and us.
I'm sorry.
That's all right.
These galaxies which we speak about, do they also have planets and stars?
Yes. Yes.
How do we know, like, take one example, you said these are far off galaxies. How do we know how many planets and how many stars are?
Very good question. It's not directly related to what we're talking about, but let me answer that anyway because it's. All right. So the question was, I'm saying that this is a whole bunch of cluster of galaxies, let's say 1,000 galaxies. Are there stars and planets in these galaxies as well? And if so, how do we know that? Okay. So how do we know that there are stars or planets in these galaxies? Stars we know because we can measure the light coming out of these stars. We can't see them directly, but we can measure how much energy these stars emit, or let's say you can look at the color of this object, and by measuring the color of this object you know that this is a star. Alright? Now, the way you measure planets is actually very interesting. There are many ways, but one of the most popular ways recently has been something which is like an eclipse. So what happens is that you have this star, and when a planet goes between you and the star, it reduces the amount of light from that star a little bit because it eclipses. And you can measure this little reduction, and it happens again and again, let's say. And so then you know that there is a planet going around this star. This is one of the ways. There are other more sophisticated ways as well. Okay, so let's come back to dark matter. So what I'm trying to say here is that the motion of light from the faraway galaxy to us allows us to measure the mass between us, and this is a huge amount of mass which is not actually seen. So we must then again postulate that there is this dark matter out there, which is not being seen, but it's there. So the third way, let's look at the fourth way by which we know that there is dark matter. We are here, okay? And when we look far away, we are looking at the universe as it was in the past. Okay, this is a very mind-boggling thing if you haven't thought about this. But because it takes time for light to travel from any place to any other place, when you're looking at a very far away point, light has taken that much longer time to reach from there to you. So when you're looking far away into the universe, you're looking at the universe as it was when it was much younger and much hotter, because the universe was small and there was a whole lot of energy there, and the universe was very hot. So when you're looking far away, you are eventually going to get to a point where the universe was so small and so hot that everything was completely ionized, that everything was charged. It was a plasma, and inside a charged plasma, light cannot travel freely. So what that means is that very far away, the universe is still very young. When I'm looking at very far away, I'm looking at a very young universe, and this universe is still very hot and ionized and violent, and light from there cannot directly come to me, because this light is still getting scattered over here, because there are lots of charged particles which are eating up the light or reflecting the light or scattering the light. At some point, the universe became cold enough that atoms could form. And atoms, as you know, are neutral. They don't have electric charge. And then the light can start coming to us more or less unimpeded. This happens quite abruptly, if you will, and therefore you can think of there being a surface beyond which the universe is too hot to be transparent. So there is this curtain which is 380,000 years away from Big Bang, and the age of the universe roughly is, let's say, 14 billion years. So this is 14 billion minus 380,000 years. So that's the distance from us to this surface, which is known as the surface of last scattering. Last scattering because light was undergoing scattering over here, and then around here the universe became cold enough that the light does not undergo any further scattering, and then it can come to us. Okay?
I have a question.
Yes.
Do you have an idea at which speed the universe is expanding?
Yes, we do have an idea of that. I will talk about that in about 5 minutes. So there's this surface of last scattering, and light is coming from that, and by measuring the properties of that light, we can again know something about dark matter. How? So what I'm saying is that there is this surface of last scattering that it has some temperature, because it's a surface, there's photons behind it which are trapped, and then this light is coming to us after the surface. And this is my big satellite called Planck out there in the sky measuring this light. Okay. This light is, by the way, called the cosmic microwave background. Alright, so what now I do is I remove the fact that this light is very uniform all over the sky. So I subtract off the part which is very uniform, and I'm only looking at the part which is fluctuating from point to point in the sky. In fact, this temperature across the sky, if you go and measure, is not exactly the same. It fluctuates by 10 parts in 1 million. So it's a very, very tiny fluctuation, but we can measure it. Okay? So we measure this tiny fluctuation, and you will ask, why is there a fluctuation? Why is this temperature not the same? Why is the early universe not exactly the same temperature everywhere? The reason is that the universe is like a little bucket of water. Okay? When it's ionized, it's like a little fluid, like a plasma, which is like a little bucket of water. And there are two things which are happening in the water at the same time. There is photons or light or heat, which is trying to make this liquid expand and go in all possible directions. This is pressure. And then there is gravitational attraction. The things are trying to come together. And so there are these two opposing forces. One is trying to take things away from each other. The other is trying to pull things closer together. And these two opposing forces, what they lead to is oscillations. So the fluid, the liquid in a bucket oscillates because you you have pushed, let's say, the surface of the water and try to push the water away, but then gravity pulls it back, and then this keeps repeating itself because of inertia. The exact same thing happens in the early universe, where the photons which are there in the universe, they have been pushed away because of pressure, and then they try to pull themselves together because of gravity, and this repeats itself. So the whole thing of, there are waves in the early universe. These waves lead to fluctuations in the density in the early universe, or density of photons or temperature of photons in it. This is exactly the same thing as, let's say, take the surface of a pond and you throw a stone, you see these ripples which propagate all over the surface. The same thing would happen in the early universe, because you have disturbed the universe by putting in pressure over there, and then it leads to these oscillations. By measuring the nature of these oscillations, you can then measure how much gravity there was, because the nature of these oscillations is dictated by how much gravity there is in the system, and this gravity is then dictated by how much mass is there in the system. Okay? And then you can go and measure how much mass is there, and this plot again is a very famous plot. What it shows is how much oscillation is there for a given distance scale. So essentially, if you take 2 points which are separated by some number of degrees, let's say 2 degrees, so take 2 points which are 2 degrees away, is it likely that the temperature at these 2 points are the same? Are they supposed to be very different, or are they supposed to be higher or lower? Measuring these kind of things actually tells you how much mass there should be. Okay? So a detailed measurement like this tells you that there are these points, these black points that you see. These are the data points which have been measured by looking at the sky. And then we know the equations that this system should obey, and then what we are able to do is say that how much matter there will be, and that allows us to measure how much dark matter there is, because we can count the rest of the matter. Okay? And that is also shown here. So for example, that same curve, what I am now doing is I am artificially changing the amount of dark matter, and you can see that this curve changes in shape. Okay? So I can go through this whole game and see for what value of amount of dark matter can I get the right shape which is matching with my observations. Okay? This is what is done, and this was done roughly about 10 years ago, and we were able to determine that the amount of dark matter you need is roughly 25% of the whole universe. Okay, so that was number 4, and finally the 5th way in which we know that there is dark matter, and this is the picture that I promised, the network of galaxies in the universe. This is a real picture, an experiment called SDS, a Slow and Digital Sky Survey. It measures how many galaxies are there in different directions and at what distance, and it again looks like this cosmic web. Okay, we are somewhere over here in the middle of this thing, and we are looking all around us. These 2 dark areas are regions of the sky where we are not doing observations, because that's where the plane, the disk of the galaxy is, and that's very dirty. You can't look through the galaxy very easily. So you're looking above the galaxy and below the galaxy. These 2 regions, these 2 things are occluded by our own galaxy. It's very hard to measure things there. And again, the shape and the nature of this web tells you something about the fact that there is more matter than what you are seeing. So you can count how many galaxies there are, multiply by the mass of each galaxy, and that tells you the total amount of mass in galaxies. But then you find that this shape actually cannot be created with just that mass that you have. You need more mass than what you are seeing, and again that will allow you to infer that there is more mass than you are seeing. So that this totally different 5 different ways by which one has found out that there is a need for this mass in the universe, which is all over the universe clustered in some way, but we can't see it. And this evidence comes from a variety of things. So what I'm showing here, this is, let's say, the solar system, which is inside the Milky Way, which is inside a group of galaxies called the local group, and which is inside the entire universe. And you can do measurements of all these different places. You can do measurements of the rotation of galaxies. You can look at the lensing of light because of clusters of galaxies which is at this distance. You can look at the structure of galaxies at the largest scales, or the structure of these fluctuations on the last scattering surface of photons, the CMB, and that's at the scale of the universe. And at totally different places in the universe, totally different length scales, one can do these measurements. And from all these measurements, what one infers is that you need more mass. So that tells us that there is overwhelming evidence for missing invisible mass in the universe, which is clustering, which is forming something like a galaxy, but we can't see it. Okay? There is one more thing in the universe.
You said 25% will be.
25%, yeah.
So established today is only 25%.
Yes, so just 2 more slides and I'll answer your question immediately. So, what I've said so far is that there is this invisible mass out there, but I haven't told you exactly how much except to state that it's 25%. A very detailed study of the pattern of these fluctuations and the shape of this cosmic web allows you to measure that number. Okay? But you also need to know about one more thing about the universe, which is that the universe is expanding. Okay? And not only is the universe expanding, it is expanding in a very interesting manner. So let's see that. So this is a picture of a part of the universe. It's just a schematic. These are not real galaxies. We just made a picture like this. And after some time, the universe looks like this if you are sitting in this galaxy. Okay? So this is a part of the sky, let's say, and I am sitting in this galaxy. After some time, this is what the universe looks like. That everything has gotten farther away. And because it has gotten farther away, and it's going farther away at roughly a constant speed, it's like a train which is going farther away from you, whose sound tells you that it's going farther away from you, Doppler shift, for those familiar, and which tells you that there is a red shift, that these galaxies are red shifting away from you. That allows you to measure how fast is the universe expanding, that these things are moving farther away from you. This is not just true of our galaxy. I'll take the same picture and put ourselves in a different galaxy, let's say this one. And we'll see that the same thing happens over there. So, let's say this is what's happening at our galaxy. Everything looks like it's moving farther away. Now let's play this same game, but with, this is our starting point, but now we live on this galaxy. After some time, this is what the universe will look like if you're over there. Now, let's superimpose our galaxy on each other, and what it looks like is that every other galaxy is moving away from you. So this experience that galaxies are moving farther away from you, this is a universal experience. Every person on every galaxy, no matter where they are seeing that the universe is expanding at some rate. This rate is known as the Hubble rate, the Hubble expansion rate. For the longest time, people thought that this was a constant rate, that the universe is expanding at a fixed speed. Okay? But somewhere around the year 2000, it was realized that not only is the universe expanding, but it is expanding at an increasing rate. That the speed at which the universe is expanding is becoming larger and larger. So there is acceleration, not only speed. Okay? That is something completely bizarre. We don't understand why this happens, but we have a name for it. We have a name for it, it's called dark energy. So the total amount of energy in the universe, of that 70% today has to be this thing called dark energy, which makes the universe expand at this accelerating rate. The rest, 30%, is made of dark matter and visible matter. Okay? So this 30% has 25% dark matter, 5% ordinary matter, and the other 70% approximately is this dark energy. So I'm not going to talk about dark energy at all, the expansion of universe at an ever increasing rate. I'm going to continue talking about this 30% over here, of which the 25% is dark matter. Alright, so another way of looking at is this picture. If this is all of the energy in the universe, roughly 2/3 or 70% is this thing called dark energy, which we are not going to talk about. Roughly 25% is this, is dark matter, 27%, and everything else that we know of, atoms, gases, everything that we are familiar with, all of the physics, chemistry and biology that we have learned in schools and colleges so far, concerns with just this 5%. So there is this entire 25% of the universe still waiting to be known. We don't understand what are the atoms of this object, and this is a big mystery. Okay? This is dark matter.
Wow. So, have you been able to calculate the total mass of the universe by this?
So the total amount of energy in the universe is related to the expansion rate of the universe. By measuring the expansion rate of the universe, you can measure the total amount of energy in the universe.
But we presume it is constant. The total mass and mass equivalent of energy.
Not really. So this is again something very weird about dark energy. The fact that the universe is expanding at an accelerating rate actually tells you that the energy in the universe is increasing. So this energy is being extracted out of something, but we don't know what that is. In fact, the right way of saying it, scientifically the more acceptable way of saying it, is that this idea of energy on universe scales is slightly more subtle, and one cannot say that this is the total amount of energy of the universe. So one has to be a bit more precise in these definitions. But for our purposes, I think it is correct to say that the energy density in a given volume stays the same while the universe expands. So the total amount of energy is indeed going up. This thing is called dark energy.
Is it something similar to what Professor Nalekar said about matter being created continuously?
It is similar in some sense, though it is not exactly the same. So there is this different model of the universe called the steady state model of the universe, where one also invokes similar ideas, but this is not exactly the same thing. Here we don't actually explain where this energy is coming from. So the equations that Einstein has allow you to write down something known as the cosmological constant term, which would give you exactly this behavior which is seen. And so we just call it the cosmological constant, or lambda, and we just say that that's what this is. But we don't actually understand what it is. We know that mathematically that's what this cosmological constant should do. That what it should do is make the universe expand at an accelerating rate. That's called dark energy. Yes.
No, they say the expansion would ever stop and whether it will start contracting depends on the mass the universe has.
Yes.
So, if the mass itself is not constant, probably it's not possible to determine whether it will ever stop expanding and start contracting.
Yes, indeed. So, I mean, these things are subject of contemporary research. There are many people who try to look at data and try to figure out if indeed this model of the universe is correct, or some other model of the universe where the amount of, let's say, energy creation will stop at some point or increase much more at some other point. And you can then use experiments to test these ideas. So, yes.
So, where does the black hole come in here? Is it inversion?
Yeah, so black holes are made of exactly the same stuff that we are made of. These are atoms, these stars which have collapsed and formed black holes. So black holes are actually included in this 5%. Yeah.
So it's not a conversion to dark energy.
No.
When you say that space-time bends in the presence of a bigger object,
Correct.
does it bend or does it appear to bend?
Well, let me say that it is measured to bend, does that make you happy? So see, physics is about making measurements, and if you measure something to have been bent, then we would say that it is bent.
But the position stays same, right?
No, so what is bent is the geometry, not and all the objects which are sitting inside that geometry.
When you say expanding universe, I think it is not the universe expanding from that slide that you showed. In the galaxies moving away, so it's only an apparent, like the apparent migration of the sun. It is, nothing is expanding, it is the moving away that makes
Very nice. It's the space-time which is expanding, but it isn't like that there is a big piece of wood which is becoming larger, indeed. But when we say that the universe is expanding, what we actually mean is that objects in the universe are getting farther away from each other, indeed. Yeah, so the question there is that has the universe always been expanding at this ever-increasing rate? No. In fact, we can make that measurement, and that's what this picture is actually showing. So here I am showing the size of the universe relative to the size now. So this is time running forwards. We are here now, and these different curves are showing possible ways in which the size of the universe could have changed. Now, if there was no dark energy, if there was nothing over here, so zero, let's say, and there was only the entire rest of the universe was made of matter, which is, let's say, 1. So let's look at the green curve. Then this is what the universe would look like. It would expand, but it would sort of slightly slow down as it expands. And in the past, it would have, be at, let's say, minus 10 billion years away from now, roughly, it would have had a size of 0, roughly speaking, which is the Big Bang. So the Big Bang would have happened here, and then we are over here now, and then the universe will continue to expand, but it would slow down in its expansion. That would be true if the universe only had matter and no dark energy. Okay? On the other hand, if you have less matter than this, so the universe does not have as much matter as we think that it does, then this blue curve is what happens. So we are over here, the size is 1 in our units now. It continues to expand at a constant rate, okay? And in the past it had, a starting point, which is the Big Bang. If you put in too much matter, 5 times the amount of matter that we know that it has now, and no dark energy, so it's still 0, then the nature of the universe is this orange curve. So we are over here. In future, the universe would collapse back into a point. This is called a big crunch as opposed to a big bang. And in past, we had started from this point, which is the Big Bang. So for a very long time, people didn't know this very big, fact about the nature of the universe. That is the nature of the universe going to be such that in future everything collapses into a single point, or is it going to continue expanding? It's such a big question about the nature of the universe. And now we actually know the answer to this question from science. We know that we sit on this red curve, where not only are we expanding, but we are expanding faster and faster. Alright?
I was just wondering about the multiple images of galaxies. Are we looking at each of those images of the same time period, or are they of different times or based on anything?
Sometimes there can be even a time delay between the two images. So let's say one of these galaxies is flaring and doing something. One of the images appears to flare earlier than the other, and from that you can again measure the difference between the two paths that the light took, and that allows you to measure how the mass was distributed. So these are the sort of things that we would use to make the map of dark matter between us and the galaxy. Thanks. Good question.
So, the Andromeda galaxy is coming towards our
Yes.
So if it is expanding, then how is it coming towards us?
Indeed, that's another wonderful question. Thank you for that question. When I say that galaxies are moving far away from each other, this from each other, that is in general true for all galaxies. But as you can imagine, I can move closer towards to my friend over here. Nothing stops me from doing that. But this is what we would call a peculiar velocity. So stars can move closer to each other or galaxies can move closer to each other, but that's something which is happening locally and it's called peculiar velocities. That's not the overall cosmological expansion. So if you have sufficient velocities towards each other, you can get closer. But on an average, the universe is expanding and typically galaxies are moving farther away from each other. I don't exactly remember the number, but I think something like 10 or 15 million, maybe billion years later, our galaxies would combine, the Andromeda galaxy and the Milky Way. But I don't exactly remember the number. But it's far away in the future.
No, but if the red line is the thing, there's no way it is going to contract again at all.
Yes, not the entire universe certainly, but two nearby galaxies,
Okay.
They can attract each other and merge together.
Now the mass energy equivalent is given by E equals mc square. Does it have a similar equivalence in the dark matter and dark energy? Or do we know?
No, actually that is indeed the reason why these names are slightly confusing. What ideally we should talk about is that this dark energy is nothing but the acceleration of the universe. We should not call it dark energy. That's a very bad name. It's a name given by one of my professors, but unfortunately it's a name that has stuck. This is better called the acceleration of the universe. But it's a long name, people don't like that. Dark energy sounds more fancy.
The acceleration has never been explained.
This is the explanation, if you will, that you need the Einstein's cosmological constant in order to explain the acceleration of the universe. Okay, so these different histories of the universe are all possible histories. There was nothing that precluded one or the other from happening. We could have lived on any one of them. And imagine people 1,000 years ago, 2,000 years ago, cavemen, perhaps asked themselves this question: what will happen to this universe, million years down the line? People probably have been asking this question forever. And they had no way of answering that question, confidently. And now we know the answer to this really big question. We know what is going to happen to the universe. It's a very depressing answer, however. The answer is that at very, very long time away from now, like in very, very great future, all galaxies are going to be so far away from each other that we would not be able to see these galaxies. So the sky would appear completely dark. We wouldn't see anything except the sun, and at some point of the time the sun would go out, it would burn out all its nuclear fuel, and the sky would be completely dark. There would be no way of knowing that there are stars out there. There would probably be ways of knowing that if you were clever enough, but if you just look out there in the sky, you wouldn't think that there are things out there. You would think that you live in this dead, dark universe. So we are incredibly lucky that we happen to live at a time where the universe looks so exciting and amazing. Okay? So this is one of those amazing things that science actually gives you concrete answers to this really big existential question of where are we going. We know the answer, it's not a happy answer, but we know the answer. Alright, so that's the first half of my talk. I have another half an hour to go, but what I have tried to tell you so far is that there is this clumpy, dark matter which is out there all over the universe. Now we have to answer the question, what is that object? And so we'll come to that, but are there any questions at this time? Yeah. We don't know. There are theories about that.
What is the God particle?
This is. We will see that. We will see what the God particle is in 3 slides from now. It's not related, but we'll see it anyway. Yes.
You mentioned once that the density of the universe is constant while it is expanding, right?
Yes.
So are we to assume that mass is created in the universe?
Dark energy is being created in the universe, yes.
It always rises dark energy, right?
Yes. So this is something weird and very different from what we learn in school, right? That energy is conserved. So, but you have to learn to live with that for now.
What is antimatter?
What is antimatter? Antimatter is exactly like matter, except that it has the opposite charge. So let's say we take an electron, so which has a charge which is negative, and you have something which is exactly like the electron, so it has the same mass, it's called a positron, but instead of negative charge, it has the exact same positive charge. Okay? So these particles have been seen, you can create them in the lab routinely, and when two of these particles, so the particle and an antiparticle, or matter and antimatter, when you make them collide, they annihilate each other and make energy. Okay? So that's antimatter, which is different from dark matter. Okay? So dark matter is like matter, it's not antimatter. Otherwise what will happen is that this galaxy which is sitting inside this dark matter would annihilate with this dark matter, and we would see a big explosion in the sky. We don't see that. So we know that dark matter is not like antimatter. Yes?
Can we use the matter and antimatter collision, annihilation to create energy and utilize that energy?
Yes, we have done that, in fact. Okay, so this brings me to this God-particle thing. So a big part of particle physics is to do exactly what you just said. That you take particle and an antiparticle, make them collide, and this energy can then be used to create any particle you want. And one of the particles that was created in this experiment in Geneva is something known as the Higgs boson. It has this fancy name, but it doesn't mean anything. It's a journalist license taken by a scientist and a journalist. But for the important thing to know about that particle is that that particle is what is responsible for giving mass to many other particles, including the electron. Okay? So the fact that electron has a mass is because it undergoes collisions with this other particle, essentially speaking. Yes? It's a convention. So the particle which is discovered first is typically known to be the matter particle, and then when its partner antiparticle is discovered, we call it the antiparticle. So for example, electrons were discovered first, and then later in an experiment people found the anti-electron, which is the positive. That's also there. In fact, these two things are related. The fact that the universe is mostly made of matter and not antimatter means that we would discover the matter particles first. Or whatever particles we are made of are the ones we would discover first and call matter. And then we would realize that there are partner particles called antimatter later on.
So you said that we are increasing at a constant acceleration, right?
Constant as far as we know, yes.
Yeah, but anything that explodes, for a while it accelerates, and then it slows down.
Yes.
So maybe we are in the first phase.
Yes. Indeed, this is a very good question, and this takes you back exactly to this one. So this is expanding, and maybe, so for example something like this, it could then collapse back. It is a possibility, but the data that we have about the acceleration of the universe by measuring the cosmic microwave background, the light coming to us from supernovae, the structure of galaxies in the universe, allows us to know exactly where on this diagram we are. And I haven't shown you the data, but if you look at the data, you will find that the data actually lies on this red line, not over here. We don't have data for this part, by the way, because we are here. So we only have data about the past, but the data falls on this red line, not on the blue line, on the green line, or the yellow line. You know, all our data falls on this red line, and that tells us that we are not going to recollapse back. We are going to continue expanding and expand at an ever-increasing rate. That's as far as we know.
How does the particle accelerator give us any clue about the origin of the universe? That is supposed to be the purpose of the particle accelerator, isn't it?
One thing that, for example, a particle accelerator could do, and I'll talk about that very briefly at the end, is that it could create the dark matter particle, for example, in the lab. You know, you collide a proton with another proton, and let's see. By the way, experiment at Geneva does not collide matter and antimatter, although there have been other experiments which have done that. This experiment only collides matter with matter, and even that can be used to make energy out and other particles out of it. By doing so, in principle, you could also make dark matter particle out of it if your incoming protons are energetic enough, and that would give you something, some clue about the universe as well. Yes.
You said nothing escapes the black hole, but I have seen photos of photos, and there has been a stream of some white
Jets. Yes, very nice. This is not directly related, but anyway, I'll answer. The question there was that nothing escapes black holes, but you've seen pictures of things which are called black holes, and then you see these big jet-like objects which are emitting from that. What you're seeing is not exactly the black hole, but you're seeing a picture where there's a black hole right at the center, and there's a lot of gas around it. This gas is falling into the black hole, but some of the gas doesn't fall in, but instead is bouncing off the black hole in this jet-like fashion. Okay, so what you're seeing is stuff which was falling into the black hole but got diverted away in this jet-like fashion, and there is this disk which is slowly falling into this black hole, and it's called the accretion disk. So what is coming out is not coming out from the black hole, but just from right outside the black hole.
How you can escape black hole?
Because see, there is a distance around the black hole which is known as the event horizon. Anything that goes inside that will not come out, but things which are outside that event horizon can come out. So the gas which is coming out is coming out from outside this thing called the event horizon.
And what is the Hawking radiation?
Hawking. So this is also related to black holes and not directly related to what I'm going to talk about. But again, so think of a big sphere around the black hole, which is known as the event horizon, and I just say that nothing can escape the black hole because the gravitational force there is so strong that even light gets attracted inside. Now, what can happen is that some particle can decay into two particles, or even outside of the black hole, just out of vacuum, a particle and antiparticle can be produced, for a very small time. These are called vacuum fluctuations, and they happen. And then one of the particles goes into the black hole, whereas the other particle escapes, because they are emitted back to back from each other. Now it would look like as if this event horizon, this sphere, is emitting this stream of particles or antiparticles, but what's actually happening is that only half of the particles are escaping, the other half are going in. So it appears as if there is some radiation coming from this event horizon. This radiation is expected to have a very typical nature. It's supposed to be very black body, like in some sense it's the same kind of energy, number of, let's say, particles for a given energy follows a certain shape which is very similar to the shape that one would see, for example, in the CMB, or let's say a very good quality light bulb. Okay, this is called black body radiation, and if we could measure that, unfortunately it's very low energy radiation, but if we could measure that, we would be able to learn a lot more about black holes, for example. Alright.
This curve is telling us something different about the age of the universe. So does that mean that with the assumption that there is more matter than we thought, it has changed our view about the age of the universe?
Excellent question. Excellent question. And the question there is that each of these curves actually ends at a different point, in past, right? So the size of the universe becomes zero at different times in the past. So what naturally this means is that the age of the universe is different depending on what the universe was composed of, or is composed of. Indeed, this is exactly how we measure the age of the universe. The fact that we say that the universe is 14 billion light years old comes from the fact that we live on this curve and we are over here. If the universe was made of something else, the answer could have been different. The universe could have been much younger if the universe had a whole lot of matter and no dark energy. Okay? Thanks for that nice question. Alright?
One more question from you.
Sorry.
After
Yes.
My elementary question, sir, E is equal to mc square and relativity theory by Einstein. So where exactly the boundary is there because in the ever expanding universe, somewhere this must be failing and the other theory takes over. Or is it the same theory, it continues to be?
Yes. So, if I may change your question a little bit,
Yeah.
you're saying that Einstein had this theory of relativity.
Yeah.
Does this theory break down somewhere?
Yeah.
We're trying to find that out. To the best of our knowledge, so far we have found no evidence that that happens. All the data that we have so far has told us that relativity works, but we have mathematical reasons to think that this theory will not work or will have to be supplemented by something else near a black hole or very early in the universe somewhere over here. So these are two places where Einstein's relativity might still hold, but we'll have to add a little bit. So something like quantum mechanics will have to join Einstein's relativity, and that part we don't understand, and that's the subject of research of something like, let's say, string theory.
Sir, one more thing. During the big crunch
Yes.
at the slope, down slope, sir,
Yes.
so where it could be some kind of oscillation or waveform that the objects are coming down and because of the heat it may...
Very nice question. Very nice question. So the question here is that this curve, which leads to this thing called the big crunch,
Yeah.
could it be that this doesn't actually stop here, but then it again repeats?
Yeah.
That's, for example, a question that you could ask. It is possible. People talk about such things. It is based on the fact that we don't understand the laws of physics at these points where the universe is very hot and very small. The same thing will be true over here. So if you change the laws of physics in a particular fashion, you can make this curve go down all the way close to the flat line over here, and then it turns back again and then bounces. So these are called bouncing cosmologies. There are many theories like that. A part of the job of a practicing cosmologist is to write down these theories and then test them using data. And these things are still, in principle, not ruled out. Okay. More questions? Yes.
So that thing may go as a true circle, is possible.
No, so what that would mean is if you want to go in a circle, then the size of the universe has become negative. That doesn't make sense. Size is positive. So what we would have is that this thing becomes another semicircle over there. Yes.
Did you talk about the M-theory?
I don't know. That's a sign that I shouldn't talk about M theory. So M theory is a certain bigger theory than string theory, but I'm not an expert. I'll not talk about it. All right. So let's move on. I think we have another 15 minutes or so. So I think. Okay. Excellent. So let's answer the question: what is the universe made of? We already found out based on previous discussions that 5% of the entire universe is ordinary matter, stuff that we know of. Then there is 25% which we don't know, which is this dark matter, and then there is 70% which is dark energy. I'm not going to talk about dark energy as I said, but let's talk about this 5% for a second before we move on to dark matter. Okay? It's really a big surprise that we are in this 5% of the universe, and we are able to understand this big universe of which we are a tiny part. This is a big surprise, that how is it that such small things like us have the ability to comprehend what's going on with such a big thing, such a complicated thing as the universe. And on the other hand, it's not a big puzzle, because we are in some sense part of the universe, which allows the universe to understand about itself. Because we are made of these atoms which were actually formed inside stars. Our atoms could not have been formed anywhere else. We know this for a fact. Our atoms had to have been cooked inside these big massive stars which exploded, spewing out their guts all over the universe, and then this atoms then cooled down and collapsed again, formed new stars which again exploded, and this happened a few times until one of these stars exploded, and this carbon, hydrogen, nitrogen, oxygen, all these elements which were created inside these stars formed a little lump which formed a galaxy called the Milky Way, inside which formed a little star called the Sun, around which there was a little rock which went around, which was the Earth, on which we formed. All of this happened after billions of years when stars exploded and spewed out their guts. So the stuff that we are made of is exactly the stuff which is sitting out there in the stars. So we are not that different from the rest of the universe. At some point we were all mixed up, and in that way it's very nice to think this, that we are very small, but we are also very big, because the whole universe is us and we are just a way for the universe to understand itself. This is a very philosophical point of view that many great physicists have taken, that this again big existential question of what is our purpose on life. Our purpose in life is a very small question to ask. A better question to ask is that what is our purpose, and our purpose is for the universe to know itself. So that's what we are here for as a scientist. Okay, so now let's move on from ordinary matter but to dark matter. And we want to talk about what is dark matter made of. What are the atoms of dark matter? So this is a question which, by the way, is kind of strange, because on one hand, this cosmology or astrophysics is a study of very big objects which are very far away. And this idea of what is something made of, what are the atoms of something, is a study which happens inside labs. You look under a microscope or you do these collider experiments like this, and naively you wouldn't think that there is any relationship between cosmology and particle physics. Right? One is done by looking deep inside an atom. The other is looking far away into the universe. Why should these two things have anything to do with each other? But now if you realize, we have come to a point where these two completely different scientific communities have to talk to each other. Because by looking far away in the universe, we have found this object, dark matter, which cannot be ordinary matter, as I will just argue in a few minutes. Okay, so the fact that dark matter cannot be other planets or some stars or black holes is based on the fact that all of these objects are either too few in number, or they are so compact that we would see a lot of lensing around it. This gravitational lensing that we saw before, we know how much of that happens. The fact that it doesn't happen all the time and in too large quantities tells you that dark matter cannot be something which is very compact. It is lumpy, but it is not as compact as a black hole from itself. So these sort of ideas then tell you that dark matter is not made of other planets or stars, or let's say black holes. Another very interesting thing is there's this thing called the bullet cluster. This is a picture that we'll go through this carefully. Alright. Now pay attention to the yellow dots. This is what you see in visible light. When you see out there, this is what the Hubble Space Telescope sees. This red stuff is what is seen using an X-ray telescope. That also sees ordinary matter. This blue stuff that we just saw, that comes from a measurement of the lensing of these galaxies again. Okay, so now let me show you all of these three things together. This is what the picture looks like. So there are these galaxies in the background. There is this red stuff which is ordinary matter, which is measured using an X-ray telescope. It's a telescope which measures X-ray light. Okay? And then I can also measure where most of the mass is by looking at the lensing that I told you about, and I paint that blue. Wherever I think that there has to be mass, I have painted that blue. Now notice one thing is that most of the mass is not where the ordinary matter is, which is this red stuff. Okay, so the ordinary matter does not really coincide with where most of the mass is sitting. The other thing to notice is that most of the mass is in this blue stuff, which is sort of shifted from the blobs of these things and a little ahead on both sides, and then this red stuff has this very sharp boundary lines. It's something weird. So this is similar to archaeology. Now this explosion has actually happened way past, in the history of the universe. What has happened is that two clusters of galaxies have collided with each other. And in that collision, the ordinary matter has actually, undergone a collision, whereas the dark matter has actually just gone through each other. They don't interact with each other, almost, like something which doesn't see or interact with each other like a ghost. Alright? And this feature is very similar to what happens when a very fast object moves through a medium. So it's a bullet which is moving through water, and then you can see that there is this sharp feature. It's called a bow shock. It's exactly the same thing that happens when you have a boat which is moving through water, and you've probably seen that there is this feature which happens right in front of the boat. It's called a bow shock, and that's exactly the same thing. So there's this galaxy which is moving through the rest of the ordinary matter, the galaxy cluster, and that leads to this bow shock. So that tells us that these two things must have collided like a bullet. And by measuring the speeds of these things, we know that how far back in the history of the universe these things would have collided. And from that we know that this is the ordinary part which is traveling at this speed, and it is slowed down because it actually collided with each other, like two lumps of clay, if you will. But the dark matter part did not interact with each other. So this is our first way in which we know that dark matter is not like regular matter, because unlike regular matter, it interacts very little bit. It has this property of going through each other. So this is something strange, and any particle that has to be dark matter must show this property. By the way, this is not the only such example. There are half a dozen or so similar collisions in the sky that we have observed that tell us that dark matter does not interact with itself too much. Okay? And yes.
So when the red part is the ordinary matter, the blue one is the dark matter. The black patches, that's like empty space.
That's like behind the galaxy cluster, where we are not able to measure things very well, but we can see the galaxies.
It's not necessarily empty space.
It's not again necessarily empty. There is dark matter out there as well, but that we are not able to measure in this picture. Okay? So now, natural question is, what is dark matter, and this is a laundry list of properties that this particle must have. So this is how, as a particle physicist, I would proceed. I have established for you that there has to be something called dark matter. Then I hypothesize that if there is such a thing, then it must be made of some things like atoms. What are those atoms? I don't know, but I know what properties that it must have. Okay? So the property is that it must be something which is stable, which does not decay, because it has been there for 14 billion years. So you know that it is at least stable for 14 billion years. It cannot have charge, because if it has charge, then it would emit light. Charged particles can emit electromagnetic radiation. So you know that it has to be neutral. It is weakly interacting, which is the same statement, is that they go through each other. Okay? So this is something that we know. And it is cold. By cold I mean that it is not traveling very fast. It is traveling with speeds of the order of 100 kilometers per second or so inside a galaxy. This we know because of the structure of this cosmic wave. If these particles were moving very fast, they would make this cosmic web very smeared out. It would look more hazy and fuzzy. But we don't see that. We see that this picture is very sharp. So we know that dark matter must be traveling very, very slowly, not very fast. Okay? So these are the 4 things that we know about dark matter. Based on this, now we have to guess what this particle is and do experiments to confirm that guess. So that's the game. Yes?
What does something mean that it's got an atomic structure?
I say an atom, but what I mean is a particle.
Because By particle, what do we mean?
It's some new particle. And
Does it have to be a particle?
so I define a particle as something which has a mass and which is sort of clumpy in some manner. So I think that definition is fairly general. There are ideas about dark matter where it doesn't have to be a particle, but I'll not talk about that.
But will follow the Newtonian this one, momentum and all that?
Yes, and this is something which obeys Newton's laws of gravity at large scales, general theory of relativity, quantum mechanics, things like that. So it's some new particle which obeys all the known laws of physics.
And this 5% you said, the matter, does it include the energy also?
No, so
Not the dark energy, the energy, mc
yes,
square.
typically those are much smaller than everything else. So, but yes, that's included too. Okay, so this is actually what is the periodic table of all known particles. Okay, so you've seen the chemistry periodic table, I think, right? The hydrogen, helium, lithium, beryllium, boron, blah, blah, blah. This is exactly the same thing but for particle physics. It's a list of all known and expected particles. So, this is the electron which everyone has heard about. These two particles together make the proton and the neutron. Okay, these are called quarks, up and down quarks. Some combinations of these make protons and neutrons. There is this other particle known as the neutrino, which is exactly like the electron but a million times lighter, and it doesn't have electric charge. So it's very difficult to detect because one, it is very light, much like million times lighter than an electron, and then it doesn't even have electric charge. So you can't detect it by putting a magnetic field and making it bend or do something. So it's very hard to measure, but we can also measure this. So this one column is known as a generation. It's a generation of particles. This is copied 3 times. These are called 3 generations of particles. And so this is all the matter that we know of in the universe. All matter in the universe is actually made of just these because these ones will decay. And then there are interactions between them. So electromagnetic interactions are given by this particle called the photon, which is light. There are other interactions which are electroweak interactions which are responsible for radioactivity. And there are interactions given by this thing called the gluon, which is what holds the nucleus together. Okay? So there are these other forces. So you're familiar with gravitational force and the electromagnetic force. There are 2 other forces. One is this strong force which keeps the nuclei together, and one is the weak force which leads to radioactivity. Because there is 4 forces, and there is the Higgs boson, which is what gives mass to all these particles and these particles. Okay? So that's the periodic table of particles. It's called the standard model. The problem is that none of these particles can be dark matter. So why? Because let's first get rid of things which don't have mass. So they don't have mass. They can't be dark matter. Let's get rid of things which decay. So all things which decay, they couldn't be dark matter. So I'm left with these particles and the neutrinos. Let's get rid of things which have charge. So all of these things have charge, so they can't be dark matter. And now I'm left with these neutrinos. Now they could be dark matter. For a very long time we actually thought that neutrinos could be dark matter. But it turns out that they are very light. As I told you that they are a million times lighter than the electron. So they travel at very high speeds. They travel much faster than what dark matter needs to travel at. And that means that these are not cold. These are what are called hot. And therefore, neutrinos can't be dark matter. So which tells you that there were none. So none of the particles in the standard model or periodic table of known particles satisfy the conditions that are required for them to be dark matter. So now you have to invent a new particle. Okay? And everything that I say after this is basically a speculation by theorists that we come up with all sorts of ideas like the gentleman over there, he was saying that, okay, can the universe bounce back? That's the sort of speculation that one would do for cosmology. But now I have to do similar speculations for particle physics in order to invent a dark matter candidate, and then I will have to go and do experiments and check if that idea is correct. Okay, so that's the game that one has to play. And so there are ways of checking. One way of checking is that if there is dark matter out there, let's say in the center of our galaxy, it's traveling at 200 kilometers per second towards us, some of these particles will come, and in principle if you have some stuff sitting in your lab, this dark matter particle can come and hit particles sitting in your lab, and if you are watching very carefully, very precisely, you will be able to see that this dark matter particle, when it hits the proton in your lab, this proton will be it will recoil and it will be pushed away. In doing so, what will happen is that this proton will heat up the block. Let's say what you have is a big block of silicon, and then this dark matter particle comes and hits the silicon atom inside your detector. Then this block will get a little bit hotter because this energy is transferred to the silicon. By measuring that, you will be able to say that a particle had come and hit this thing. Now this will happen very, very rarely. Also, there are whole lot of other particles which are noise, which are coming and hitting your detector. So what you have to do is you have to go to a place which is very, very well shielded from other disturbances. So typically what is done is that you go underneath a mine. So when there is a kilometer of earth above you which absorbs all these charged particles, and only neutral particles which are very weakly interacting can go through the 1 kilometer earth cover that you have, of which a fraction would be dark matter particles, and by measuring that you would be able to determine how much dark matter there is in our neighborhood and the fact that there is such a thing. So we have been trying to do that. These experiments have been going on, and what is, again, I want you to get a sense of the typical thing that a theorist or an experimentalist is looking at. So these are the kind of things that we make, these pictures, which tell us about the state of knowledge or ignorance about dark matter. So here I am showing you the mass of dark matter in some units, in the units of the proton mass. So this is 100 times the mass of the proton, this is 10 times the mass of the proton, and here I am showing is how much does dark matter interact with protons, let's say. If the interaction strength is somewhat large, then we know that we would have observed some of these recoils in our detector. But the fact that we have not seen any such recoils allows us to say that dark matter, for a given dark matter mass, the amount of interaction has to be less than this. Right? Because if the interaction was more than this, we would have seen it. So the fact that we haven't seen these interactions tells us something about how strong these interactions are. And this is how we learn about the nature of dark matter. What will eventually happen is that we will start seeing some of these collisions of dark matter and protons in the lab, and we will find a blob like this on this picture, which will tell us that the dark matter mass is so much and it has such and such interaction strength. Then we have learned something new about dark matter. We now not only know that there is this invisible stuff out there, we have learned that this is a particle with a mass which is roughly 100 times the mass of the proton, and which interacts at some level, let's forget about those numbers for now, for the moment. But roughly speaking, we've learned something about the nature of dark matter. So that's the hope, that these experiments will eventually see something like this. What is shown here, unfortunately, are flukes. So we saw a bunch of events in some detector, but it turned out by doing more precise experiments that they were wrong results. That you had seen something which you had interpreted as dark matter, but it turned out not to be correct. So this also happens in science. You do some experiments, you make mistakes, other people correct your mistakes, and then you move on. You do better experiments. That's part of science. It's not that scientists are always right. It's perfectly alright to make mistakes. Alright, so the other way of finding out about dark matter is this thing called dark matter annihilation. So there's a galaxy out there, dark matter particles can interact with each other and annihilate, and then you can see the products of that annihilation using a satellite.
What do you mean by annihilation?
What I mean is that two dark matter particles can meet and make an electron and a positron by getting rid of all these dark matter particles.
They change the form from dark matter to
Correct, ordinary matter by interacting with each other. Now usually this only happens when there is one particle and one antiparticle, but there are theories which tell you that dark matter is its own antiparticle. In that way it's a little special. It's a theory, this may not be correct, but if this is correct, then this is predicted, and then by looking at such a thing, I can go and test this theory. So this is the reason why we do this experiment. Okay? So once we do this experiment, what we can do is we can look at different sources. So there is dark matter accumulating inside the sun, there is dark matter accumulating inside the Milky Way, nearby galaxies, inside galaxy clusters, or even at the biggest universe scale. Okay? And then they can meet and give you a bunch of particles which could be just charged particles like electrons or protons, they could be neutrinos, or it could just make light. And so depending on all of these things, you could be looking at the sun using an optical telescope or X-ray telescope, you could be looking at the Milky Way using a neutrino telescope, you could be looking at galaxy clusters using a cosmic ray telescope. And so depending on this, you can do lots of different experiments, and people have done that. There are literally dozens of experiments which do this. And again, these pictures are exactly like the one that I just showed you. Dark matter mass here, and this interaction strength over here, and these lines are telling you what is the allowed interaction strength. And so far we have again not found dark matter. We have only been able to say that the strength has to be smaller than this. Okay, so we have ruled out this entire region above the line, and we know that dark matter mass, whatever it is, it has to have an interaction strength which is somewhat low, so it's weakly interacting. That's what we are learning. Okay?
Where do the antimatter come here? Matter and antimatter?
This has got nothing to do with antimatter per se. I mean, in principle what can happen is that if dark matter was antimatter, then it would come and annihilate inside your detector and you would see that. So you could, for example, say that the total amount of antimatter out there in the sky is smaller than this number. You can make such statements based on data.
So what is the present understanding of antimatter now?
That out there in the universe, the amount of antimatter is very, very small. I don't exactly remember the number, but in the lab you can make quite a bit of it, as much of it as you want actually. Okay, so there are other searches for dark matter. There are other particles, so these are all hypothetical particles that people invent, and then people figure out what experiment will you have to do in order to find that particle. There is this particle called the axion, which one is looking for, and then all these things are then again showing you what part of the, what we call a parameter space is ruled out. And again you look at the mass of the dark matter particle, the axion, and the interaction strength, and all these things are ruled out. So we are doing these increasingly more precise experiments, trying to look for dark matter, and the hope is that eventually we will come and find dark matter at this point, something like this. So this is an adventure. You don't know a priori, before you have actually done the experiment, where or when you will find dark matter. But you have to do this exercise, you have to go through this whole process optimistically, and then eventually you will find dark matter. So I hope that answers your question. Certain things are serendipitous, like Fritz Zwicky found that rotations of, let's say the motion of galaxies in a cluster led to the hypothesis of dark matter. This was almost an accident. He wasn't actually looking for that. But now that we know that there is dark matter, finding out what it is, it's a much harder job. Okay? There's also this experiment out there in CERN where we are colliding things and trying to make dark matter in the lab. Also, there are more subtle things like you measure the shape of galaxies. So here, what I'm showing here is the distance from the center of the galaxy, and this is the density of the galaxy. And depending on what kind of dark matter you have, this density is supposed to be rising like this, or it can become flat like this. Measurements say that it is more or less flat, which is then telling you something about the nature of dark matter. Yes?
your previous slide, you said you're trying to make dark matter
Yes.
in the collider.
Yes.
But if you don't know the nature of dark matter, how can you detect something?
That's actually a very interesting thing. See, I told you about dark matter annihilation. When two dark matter particles was making E plus E minus electrons and positrons, for example, or some other particle. The opposite is also possible. Now it is possible that dark matter is of such a kind that when you collide two protons, it will never make dark matter. This is possible. But we have to nevertheless do this experiment to find out whether or not this happens. So the hope is that this will be possible, but this may not be possible. So, but one has to do the experiment. Alright, so one can look at the structure of galaxies, and by doing all these different experiments, now what we are trying to do for the last 30 years or so is we are trying to find out about the nature of dark matter. So let me summarize. I have told you that there is evidence for dark matter at all possible scales in the universe. Okay, and we know this from a variety of different observational facts, from rotation of galaxies, from motion of galaxies inside a cluster, from bending of light around big clusters, from the nature of the cosmic web, from this cosmic microwave background. All of these things are telling us that there is dark matter. And then now we are trying to find out what is the nature of this dark matter particle. And this is proving to be a very difficult exercise. We have tried many things. These are different theoretical ideas for dark matter. And we have tried many different things. For example, collisions of dark matter and ordinary matter in the lab, annihilations of dark matter out there in some object in the sky. You can try to create dark matter in the lab. You can check if the galaxy shapes and numbers are correct depending on dark matter properties. And by doing all of these theoretical and experimental calculations, we are trying to find out the nature of dark matter. So this is an ongoing process, and hopefully, 30 years down the line, when one of you will give Mumbai Local, maybe you will be talking about how you discovered what the nature of dark matter is. So with that, I will stop. Thanks very much.
Do we have any questions?
Yeah. Can you throw some light on the black hole?
Black hole?
Yes.
A black hole is an object which is very dense and very massive. So you take, let's say, something like a star and you compress it down to something which is much, much smaller than it. So for the sun, I think you would have to compress it down to something smaller than a kilometer in radius, let's say. Okay? Once you do that, the density becomes so large that if you go close enough to it, there is so much mass so close to you that the gravitational force is very, very strong. It's so strong that any light that you emit, let's say you have a torch and say I'm standing right at above the black hole and inside its horizon, and I'm emitting light above like that, this light will not be able to go like this. It will go and then it will bend back down just like an apple falls down on Earth. This can only happen near very massive, very dense objects like black holes, and that's what essentially a black hole is.
Because they always say universe is a black hole.
No, I wouldn't say that. The universe has many black holes. There are black holes in the center of the galaxy, for example. But the universe is the universe. The universe has galaxies, stars, and us, and black holes.
No, they used to say the matter is crushed out of this universe and goes into another universe.
These are very speculative ideas, yes, one could talk about them. Yes.
I don't have a physics background, but from what I know, if you can't observe, then how can you say from a quantum mechanical whether something can escape or not? You can't observe something which is inside.
Indeed.
Calculations.
I'm sorry?
She's agreeing with it.
I'm sorry?
She's agreeing with it.
Alright. No. So indeed, we don't really observe dark matter directly. Is that's what you're hinting at?
No. Within a black hole, if you can't observe within the event horizon, how do you know whether it's there or not? Because from quantum physics, if you have not observed it, it can be anywhere in the universe.
Yes, but what you can nevertheless say is that there is some matter inside it which is causing light to bend like that. Right? Because you're observing the light outside. Now, if you want consistency with the laws of physics, you have to demand that there is matter inside. thing, whether you want to call it a black hole or not is a different question.
But you can't say that nothing can escape because it can. You may not observe. I agree with the fact.
No, but if it,
I agree with the fact that light is having that kind of a, it's not passing. But if you can't observe some matter, maybe somewhere else you may not have seen it.
I don't quite understand what your conclusion is, but maybe we can talk about that.
Living here upstairs.
Yes.
Might be a wave. Why is it so important to study moments after the Big Bang and not at the Big Bang?
At the Big Bang.
Moments after the Big Bang. That's what people keep talking about. A very few fractions of seconds after. Why is it so important?
As opposed to?
At the Big Bang.
So,
at the time of Big Bang.
The Big Bang is anyway, a very small, almost infinitesimal time, if you will, so doesn't tell you much. So you have to study the time around the Big Bang, if you will. But more importantly, we do not expect our laws of physics to hold too close to the Big Bang. We expect our laws of physics, especially quantum mechanics and relativity together, to hold only up to a certain, time back in the future. When the universe was too small, then we know that our laws don't work. So that's also another reason why we don't want to talk about things which are too close to Big Bang.
I have a simple question. Is light particles or waves?
Well, excellent question. It is both. Okay? Quantum mechanics tells us that not only light, but everything is both a wave and a particle. In fact, there is no difference between a wave and a particle. How is it true? So think of what is a wave. A wave is a disturbance in something, right? So the way we think of a wave is that there is this oscillatory picture like that. Typically when somebody says a wave, it is a oscillation which is like this, which is a big oscillation like that. But think of making this oscillation somewhat more localized. Like we have two oscillations here, very tiny oscillation, and then we have an oscillation like this and like this. Would you call this a wave or a particle? It's still a wave, right? So few oscillations. Now make these oscillations smaller and smaller so that there is no disturbance anywhere else, but there is disturbance at a very specific place. That looks like a very localized object. That's a particle. So there is a continuum between particles and waves. Okay? And what quantum mechanics tells us is that every particle is a wave, every wave is a particle. The question is how much wave-like is it and how much particle-like is it? Light has this very nice feature that it can exhibit both particle-like behavior and wave-like behavior. Ordinary objects mostly exhibit particle-like behavior unless you go and look at it under a microscope, things like an electron microscope, which is the realm of quantum mechanics. And there you can see that things like electrons, which you think of as particles, also behave wave-like.
I was just thinking about going back into time. They were ancient astronomers, astrologers. Did they really worry about the dark matter? Did they ever bother?
I don't know.
There would have been some reference.
It would be interesting to ask. Many cultures, especially ancient Indian astronomers, had a very amazing sense of what the universe is like. There were other cultures which had much more, conservative ideas about, the universe only being, 5,000 years old. But in India, Indian philosophers or scientists, if you want to call them, they believed that the universe was indeed 10 billion years old. So we think that this is a coincidence, at least I think so. But they had the number roughly correct. There are calculations of the age of the universe in scriptures, and the number, if you convert to modern units, is 10 billion years. It's kind of amazing that they had a sense of such large numbers. So astronomers such as Carl Sagan and Narlikar have talked about how amazing it is that then called Hindu astronomers had a sense for such large numbers, because most other cultures, they could not imagine such large numbers because they did not know of zero. Now once you know zero, you can write large numbers very easily. So that's why Indian culture had this idea of very old universe. And now ideas like dark matter and dark energy are even less intuitive. You wouldn't think that there something out there in that dark part of the sky. There is no reason to think unless you know a lot about the laws of nature, which we know after 300 years of studying science. So I would say it's unreasonable to expect that the ancient observers and philosophers would have thought of dark matter or dark energy, but they certainly thought of questions of what will happen to universe much later than us.
What is the age of the solar system? 4 billion?
Now you've caught me. These are the sort of things that I don't remember. But I would guess a billion years or so.
The Earth is 4 billion.
The Earth is 4 million? Billion? Okay.
But it will last for another 2-3 billion years.
Again, from what we understand, the universe is going to expand. So.
Alright.
Is there any reason to think there's when you say dark matter particle, is it it's only one particle?
No, indeed, that's a great question. So when we say ordinary matter, we have many particles in ordinary matter, right? We have protons, we have electrons. So it's not reasonable to expect that all of dark matter is one particle. But if you think about it, most of the ordinary matter is actually composed of protons. Although there are an equal number of electrons, electrons are much lighter than protons, like 1000 roughly in mass.
What about neutrons?
Neutrons and protons, let's say. Okay. Actually, most of the universe is made of hydrogen, mostly just protons. Okay. So the universe, although it has many particles, in terms of its mass, it's overwhelmingly just protons. So it could be something like that for dark matter also, and it could be just one particle, or it could be many particles. We don't know.
How long are we going to last?
I mean, you mean how long are we going to last here in this talk? Or? No, I know, I'm just joking. See, these are depressing questions. You should not ask these questions. The Earth will last only as long as the Sun is able to provide energy to us from a safe distance. So indeed what will happen is at some point of time the Sun will run out of its hydrogen fuel and it will become a big red giant star. It will become so big that it will eat up the Earth. So that's the end of Earth, if you will. We might actually end much before that because of climate change on Earth. But
even a meteorite might destroy the life.
I think that's a great idea. But so far I think that's still hard. We don't know. Maybe that's what we will have to do.
Okay.
Yes.
Is it okay to ask something about time?
About time?
Time, see, the same watch that you wear here, if you take it to the, it runs slow. Why is it so?
It's a very good question, but it's a very good question. The question is that relativity, special relativity says that if you take a clock and you're moving with some, let's say, constant velocity in some direction, your friend who's standing over here will say that your clock is running slow. Okay? So there's somebody, let's say me, I'm running at some speed like this. All of you will find that my clock is running slower. Okay, so this is a fact. How do we know that this is a fact? Because we know that there are these particles, let's say, which are not stable, which decay, and they have a very well-defined lifetime. So they decay within a given time. So if they are standing out there in the lab, they decay within some time, let's say whatever, 1 microsecond. But if you make them move at a fast speed, then you see that they don't decay within a microsecond. They decay after a very long time. So we know that this is a fact. Why does this happen? This is very hard to explain in words. This has something to do with the nature of space-time. Special relativity tells you that clocks run slower when you are seeing it from a different frame, which is at some relative velocity. One way of understanding this is the following, that how do we measure time? We measure time by actually looking at something, let's say like a watch, or for simplicity, let's think of a pendulum doing this. Now when something is moving far away from you, the way you will see the pendulum is that you will have to send a light beam. The light beam will reflect off the pendulum and come back. And when it comes back, then you know that you have hit the pendulum once, and then there's another photon which has to do this, and you have to see the pendulum go through one full oscillation like this. But if it's going farther away, it takes you a little bit longer to send that light beam and bring it back to C. And this effect looks like as if the pendulum is running slower or the clock is running slower. So what is happening is the fact that the speed of light is constant no matter what. And this forces clocks to become slower when measured using light. In fact, it's not just using light. Any way of measuring time or space has these properties. That space looks like it contracts, space looks like it contracts and time looks like it dilates. So clocks run slower, rulers become shorter.
If you draw a clock in a black hole, then you will find that it's permanently falling.
Yes, indeed. That's another very interesting thing, that people think of falling into a black hole. This, by the way, not settled. No one understands what will happen when you fall into a black hole. There are very, very important scientists debating about it very, very fiercely. But it is indeed understood that the process of falling into a black hole through the event horizon, that slows down time very, very strongly. So in fact, if you observe from outside that there is a black hole, a region around the black hole, and some star, let's say, is falling into this black hole or some other object, you will actually never see it go through the event horizon. I mean, time for that object will slow down so much that you will only think it is just asymptotically approaching the event horizon. You will actually never see it go through. So indeed, that happens as well. Yes. Yes, indeed. So the question is there any research going on at IUCA, which is in Pune? It's an inter-university center for astronomy and astrophysics. It's a great place if you are in Pune to go and talk to people working on astrophysics and cosmology. There's a lot of work going on in these things. They are mostly more interested in observational and experimental aspects, although there are a lot of theorists as well. Professor Narlikar used to be there. Indeed.
Do you have an observatory in TIFR here?
No, so TIFR in Colaba, this is a very bad place to have an observatory because there's so much light pollution and things you can understand. But TIFR runs observatories elsewhere. So TIFR has this thing called the Giant Meter Wave Radio Telescope, the GMRT telescope, which is near Pune. It's a radio telescope which looks at the universe. We run other telescopes. One is in Ladakh. There are other telescopes in Uti. So, and we are also part of international experiments, where the experiments are actually held, let's say, in Geneva, or in principle some of them will be built very soon in Australia or Africa. And TIFR scientists are part of those experiments. They go there to do their observations. And so that's how science is now done on a global scale.